As your moderator, I realize that I stand between you and lunch, so I'm going to get this going as soon as possible. Our first speaker today is Dr. Fred Goldberg. Dr. Goldberg is an associate professor at the Royal Institute of Technology in Stockholm, Sweden, and he's been an authority on polar history and exploration. He's been an invited lecturer at many universities. He's published many papers and in 12 different languages, which I find quite impressive. He has participated in many international studies and was appointed by the Secretary General for the International Climate Seminar at the Royal Institute of Technology. And he's a lecturer to a wide variety of groups. So without further delay, Dr. Fred Goldberg.
Thank you very much. Ladies and gentlemen, I will try to give a very quick paper if we think the planets and the sun control our climate and the CO2 in the atmosphere. There might be some overlap with previous speakers, so I hope you will forgive me, because I didn't know what slides they were going to show. I will talk a little bit about the chemical and physical properties of CO2, the climate effects of ocean currents, what makes the ocean currents change direction, which is a very interesting point, and the climate effects of planets and solar activity, which is a very big subject. I will be quite brief there. Okay, carbon dioxide. The amount of carbon dioxide has increased from 290 to 385 ppm. That means that of 10,000 air molecules, one nitrogen molecule has been replaced by CO2 molecule. Does that change the climate? Well, from a simple engineering point of view, I don't think so. CO2 is a greenhouse gas because it absorbs IR radiation from the ground. But the greenhouse expression, I think, is incorrect because we don't have a glass roof on our atmosphere, but that is what we have in greenhouses, making things warmer. But water vapor is the dominating greenhouse gas, as we heard earlier today, and it represents approximately 95% of Earth's total greenhouse effect. The greenhouse effect from CO2 in the atmosphere is approximately 1%, but there might be some scientists arguing that number, but doesn't change the facts. What is important to look at is the absorption spectrum. And here we can see that water vapor takes care of a large piece here. Here's a very tiny 4.2 micron where the CO2 absorbs. And then we have a large area where the water is absorbing the IR energy. And then we have the 14 to 16 micron CO2, which is also overlapping with water vapor. So if the CO2 is increasing, does that mean that its absorption increases? Maybe not, because it might be the water vapor that picks that up, because they overlap. But nevertheless, the CO2 absorption is very small compared to the water vapor absorption. What is also important to educate the public with is the fact that the absorption is logarithmically declining with increasing CO2. And this diagram shows that if we go back 100 years, we were here on the red line, and with the increase of 100 ppm, we are on the middle line. We see a very tiny increase of forcing. And when you compare this space here, you should remember that we are not at zero here. So it's a very minor change. And if we increase the CO2 and doubling it, there's still a very small increase of forcing. And this can also be shown in this diagram, where the first 20 molecules out of 1 million takes care of 1.6 centigrade warming, the next 20, 0.3, and so on. And if we then look, what is happening is that the last 100 years, we have had an increase of 0.1 centigrades from the last 100 ppm of carbon dioxide, and if we continue to increase, it will have a very minor temperature effect. Another factor which was mentioned earlier today is that carbon dioxide is readily soluble in water, fresh water, but if we go to seawater, it absorbs 73 times more CO2. And Tom Segelstad explained all the processes involved there, so I will be quite brief here. But what is important to remember is that there is a huge amount of processes taking place in the ocean, and the exchange between the ocean and atmosphere is 15 times higher than our human emissions each year. And if you want to model what's going on in the ocean, here's your help. This gives you an idea of all the different aspects to take into account. So I wish you good luck modeling this. Well, as you probably know, because you're all experts, the atmosphere has about 750 gigaton carbon dioxide, and the oceans has 50 times more, and the exchange between ocean and atmosphere is 90 to 92 gigatons. The biosphere has an exchange of 120 gigatons, as this diagram shows us. And if we then put together the biomass absorption, 121 gigaton, the oceans 92, that shows that 28% of all carbon dioxide in the atmosphere is absorbed by the oceans and biomass each year. That means that in 4 to 5 years' time, all the carbon dioxide in the atmosphere has been circulated through oceans and biosphere. How do we know this? Well, one very good way of looking at this was the Russians helped us quite a bit. They blew off a couple of nuclear bombs. And that increased drastically the amount of carbon-14 in the atmosphere. And the Norwegians had a very extensive program monitoring the carbon-14 amount in the atmosphere. And this diagram shows that after a couple of bombs, we had over 1,000 per mil carbon-14. And then it drastically was reduced down to our normal levels. So we can tell that in 4 or 5 years, it was down to half. Another look at the amount of carbon dioxide that we humans have produced in the atmosphere is by looking at the distribution of isotope carbon-12 and carbon-13, which was also explained this morning. And it shows that the human contribution to the atmospheric carbon dioxide is only 4%. We learned that the carbon dioxide has increased very rapidly and dramatic in the last couple of years, and you often see this diagram. But you can also do a lot of tricks with diagrams, as you know, almost as good as statistics. So you can also show the same diagram like this. It doesn't look that very dramatic anymore because we put 0 in the corner down here. So the question is this increase natural or human caused? Well, let's take a look at what's happening in the world around us. Here we can see in the upper curve the sunspot numbers. And it seems to me that there is a very good correlation between the sunspot numbers and the global sea surface temperatures. And as I pointed out, when we heat up the oceans, they release carbon dioxide. When the oceans get warmer, they have less solubility for carbon dioxide. So here we can see a good indicator of why there has been an increase of carbon dioxide in the atmosphere. This happens along the equator primarily, where the sun is most intense against the oceans, warming the water. Around the equator, we have cold ocean water coming from the bottom up to the surface, and it is carbon dioxide rich, being cold. And then when it's heated up, it releases carbon dioxide, as you can see on this diagram, between 18 degrees south and north of the equator. Beyond those latitudes, you see that the oceans are absorbing carbon dioxide, and the colder the water is, the more it absorbs. This nice diagram shows us where it takes place. We can see that along the equator, you see there's a lot of degassing of the oceans. The light colors show degassing. The darker colors show absorption around the world. So here you have the cold waters. The Antarctic, they cannot measure it because there's a lot of ice, and also the same in the Arctic. But in the summertime, there's a lot of carbon dioxide absorption because of the cold water. Some years ago, there was a sea expedition sailing from the Caribbean to Buenos Aires along this path, and they measured carbon dioxide along the route. And it's interesting to see how the measurements changed. We always hear that the carbon dioxide is evened out around the world, spreading very fast, but it isn't quite that. More accurately, the levels are different. So here we can see a big jump of carbon dioxide over the equator where the water is warm. And because the oceans are here releasing carbon dioxide, it is not absorbing. We hear every day alarming reports that the oceans are acidic or becoming acidic because they cannot absorb any more carbon dioxide, but that depends where you measure. And I think NOAA's most stations are placed along the equator where the oceans are always releasing carbon dioxide. So I think they got the whole process wrong when they say the oceans are getting acidic. And here we can see how the values are dropping down where they reach colder waters near Buenos Aires. Lance Andersby in Australia, he did this little interesting diagram comparing the CO2 changes with ocean warming, and using some smoothing technology with the 21-year magnetic cycle, solar magnetic cycle, and a 12-year monthly moving average on the CO2 from Mauna Loa. You got two identical curves on top of each other, which clearly shows that the warming of the ocean is releasing the carbon dioxide increase we are registering. Ernst Georg Beck in Germany, he went back in history and looked at all the carbon dioxide measurements, and they look very different from ice core data, as you can see. The red line here shows the carbon dioxide measurements, and they follow fairly well the temperature changes. And we know that in the 20s and 30s we had very strong warming, and we can also see that there is a strong increase of carbon dioxide in the measurements here. Here we have the ice core data, and if you study the technology of measuring carbon dioxide in ice cores, you will find out that it's not possible to get any accurate measurements. If we look at the short period, we can see here, here's Martin Hertzberg diagram, that during the Depression years, the amount of fossil fuel burning dropped 30%, but at the same time, the temperature increased, and also the amount of carbon dioxide. We see no correlation between carbon dioxide doing any warming here. I put this diagram together showing the emissions since 1980, this red line, and the changes of CO2 in the atmosphere, the anomalies. We don't see any correlation at all here. I cannot, at least. Well, let's have a look at the climate effects of ocean currents. We have a major current coming up to the north, the Gulf Stream, and here we have the thermohaline effect as part of what's going on. And cold water, saline rich, is going down at the bottom and surfacing in the Pacific, where it's warmed up, releasing a lot of carbon dioxide. And here we have, here I put together a table of the CO2 increases per year. And the year 1991-92, we had a big Pinatubo eruption, which would make you think that that year must be the one that released, that increased the carbon dioxide the most. But to my surprise, it showed the lowest value of carbon dioxide increase. But 98, we had a super El Nino that gave us the highest carbon dioxide in the atmosphere, and that was because of the heating of the ocean there. And if you plot how the anomaly of CO2 was, you can see here that it coincides very well with volcanic eruptions, two here and the Pinatubo here, and the peaks going up are El Niños and La Niñas are down here. And if we put the temperature into here, we can see that it's the temperature changes caused by the ocean currents and volcanic eruptions that is changing the amount of carbon dioxide released. And this diagram shows us that there's a 3-month lag between the change of temperature and the change of carbon dioxide. This shows us the sea surface temperature in a very nice way, and we have a beautiful La Nina here with a dark blue area across the Pacific. The oceans consist, 70% of Earth's surface are ocean, and they are, of course, the major recipient of our solar energy. And ocean currents of warm and cold waters, such as El Nino and La Nina, has a short-term global impact on Earth climate and the CO2 in the atmosphere. We're talking about 1 to 2 years effect. Important currents are PDO, the Pacific Decadal Oscillation, the southern El Nino, the Indian Ocean Dipole, often responsible for the very severe droughts in Australia. We have the Atlantic Multidecadal Oscillation, to some extent controlling the speed of the Gulf Stream in the North Atlantic. Oceans store 30 times more heat energy from the sun than the atmosphere, which is important to remember. Other heat sources are underwater volcanic activities, but they are minor. In 1998, we had the Super El Nino, which came out like this on the satellite images. And it comes out like this on our temperature diagram, very visible. And then we can see the blue areas are being La Ninas, so they alternate back and forth. January 14th, we had La Nina, which was quite bad for the farmers in California. It ruined their whole citrus harvest to the cost of $1.6 billion, and that might have triggered the financial crisis. It would happen anyway, but something must trigger it. And it's very likely that this happening was the cost of starting the ball to roll. I consulted one of the world's leading economists on this. And I was 2 days later in Tucson, Arizona, looking forward to play golf in a nice sunny day, but I woke up with no water in the shower. All the water pipes had frozen overnight, -5 centigrades, which had never happened in Tucson, and the cactus froze and broke off, as you can see here, and all the grapefruits were frozen and bounced like tennis balls when they came down. The Pacific Decadal Oscillation is a very important current for our climate, as we on the Northern Hemisphere see it. And it can be positive or negative. The positive mode pushes warm water towards the American North and South continent. And in 1977, it was a major climate shift when the oscillation switched from minus to plus, as you see here. In late April 2008, the fruit harvest in Nevada County in California was destroyed by cold weather, and the reason was that the PDO switched to negative. And that also had the effect that there was no more warm water being pushed up into the Arctic basin. That has been the major reason for the declining amount of sea ice in the Arctic. It has been the warm water pushed up by the PDO in the positive mode. Now it's changed to negative. Now there is much more ice in the Arctic, and it will be building up for the next 25, 30 years because this oscillation doesn't bring warm water into the ocean there. This switch of PDO can be most readily felt in Alaska. So here we can see when it switched 1977, you had a 10-degree Fahrenheit average increase of annual temperature in Kodiak, and a similar situation in Nome. And after that, it's been slowly going downwards. So it's very interesting here to compare the PDO cycles with the temperature cycles. We see here that we had a cooling period down to 1910. The PDO was negative. 1910, we had a rapid increase of temperature to 1940. The PDO was positive. It switched in 1940 to 1977. As a cooling period, we all know we were going into an ice age. And then it switched 77, and it went up to last year. Now we know what's going to happen. What causes the ocean currents to change direction? That's a very interesting question. I'm just speculating with what I'm telling you now, so it's not the scientific truth, but it will be interesting to discuss with you. Perhaps the changing rotation speed of Earth is the cause. Most people don't know that the rotation of the Earth is changing. It's not constant. It speeds up and it speeds down. It's about plus minus 200 milliseconds. You won't notice it when you wake up in the morning, but it's there, and it might have an effect. And it's defined as LOD, length of day. And here's a diagram I found showing how it has been changed over the last 400 or 500 years. And the issue is, what causes this? We aren't quite sure, but I have some clues. This is the most interesting diagram of my lecture that I found. It shows a very high correlation between the change of Earth rotation speed going up and down. It coincides extremely well with the PDO cycles. So my thinking is that the change of speed creates the change of the PDO. And it's about 10-year lag between the two, which means that when Earth is slowing down or speeding up, there will be some turbulence at sea bottom, and that will then slowly be carrying up to the surface over a 10-year period. And it shows that if the LOD increases, the Earth rotation slows down, and we have a positive PDO because the water is pushed forward. It's like having an aquarium with water that you are moving down with a flat surface, and if you suddenly slow down, the water will move forward and go over the edge probably in your aquarium. And same thing if you speed up, it will move to the other side. Well, moving to the other side means Earth rotation increases and you have a negative PDO considering the shape of the continents. Well, what makes the Earth's rotation change? Well, I believe it has to do with magnetic force from the sun, but probably also from Jupiter. I've consulted some astrophysicists, and they tell me that Jupiter has a very strong magnetic field. So that should have some influence both on the sunspot frequency and intensity, but also if you consider Earth as an electric motor with a magnetic field, if you push another magnetic field onto Earth, it should have some influence of speeding up or slowing down our rotation. What is also maybe not known to everybody is that the sun is not the center of our solar system. The center of mass is outside the sun position, and the sun is wobbling around this point. And it could be a factor that this wobbling of the sun changes the magnetic field towards the Earth. The sun radiation varies with rotating speed of surface plasma, intensity of sunspot and its number of cycles, and varying radius is one of the latest discoveries. The solar radiation consists of visible light, infrared and ultraviolet radiation, ultraviolet to X-ray radiation, and maybe the most important for the climate issue is the magnetic radiation that we call the solar wind. This is what the sun could look like when it is active and throwing out a lot of magnetic X-ray stuff. We call it the solar wind. And there's also a theory developed by Svensmark that when the sun is very active, we have a stronger magnetic heliosphere protecting Earth from galactic cosmic rays. But when the sun is inactive, we have cosmic rays coming into the atmosphere, and it will create more clouds. And 1% change of clouds makes 1 centigrade change in the atmosphere, which is significant. Here we can see examples of a very active sun, which gives us warming, of course. And it's called coronal mass discharge, what we just saw. It enhances the magnetic field, and we have less clouds. I'm running out of time, so I will jump here. We can see the solar cycle length coincides very well with temperature anomalies. And this book is worth reading, written by Henrik Svensmark in Denmark and Nigel Calder. We have solar cycles. We have the first 3 ones. They are multiples of each other: the sunspot cycle, the magnetic cycle, and the Goldberg cycle, which I think is quite important. And then we have the 265, 20, and 1500-year cycles, which also are multiples of each other. We have an average sunspot cycle of 11.2 years, and what has happened now is that we have here the little ice age. We can see the solar activity was here very low, and it's been going up here. But now the sun has been inactive for 2 years, and it's at this level. We might encounter the climate at 1810, 1812, which was very, very cold. We had one sunspot a few weeks ago, which belonged to cycle 23. The 24th cycle is waiting, and we've been without the solar cycle for 2 years now. Well, I'm running out of time. I'm almost finished. I want to finish by mentioning that the combination of the PDO cycle being negative and the sun very inactive, we are at this point here, and summarizing the different cycles, we're heading in for a very cold period the last coming 30 years with increasing ice and growing glaciers. Thank you very much.
Thank you to our speaker, and we have time for 1 or 2 questions. Sir.